Welcome back. Now you may have seen this rig in a previous video, but this is a DC servo motor. It's being digitally controlled using a myRio, although you could use a microcontroller. This is particularly useful though, a myRio, because you have a graphical user interface. If you wanted to do this with a microcontroller, you'd need to use something like Visual Studio to link it in. So LabVIEW is already built in, and it's got an FPGA in it as well, and that has advantages. And how this works, if you looked at the previous video, is it's a DC motor with a mass on it, fairly standard, and an encoder, a quad encoder, and the set point is another encoder, and this is a pulse width modulation system here. So the PWM comes out of the myRio and goes into the H-bridge, which goes into the motor. It's quite straightforward, and there's feedback from the position, so you're controlling the angular position. That's to say it's a position servo, not a speed servo. Set point is identical to the set point controller is identical to the, if you like, the potentiometer is a quad encoder. And if I turn one, the other one mirrors it beautifully. You can keep turning it round. So I go past 360, unlike the old-fashioned potentiometers, which only went round maybe this sort of small swing like this. It follows it all the way for many, many turns. Many as I like, in fact. It runs off a 12-volt motor, and as I change the set point, you can see the PWM here changing. There's not much DC there, and it's changing to the maximum DC as it changes here. Now, what I'm going to illustrate in this video is stability of such a system. It's reasonably well damped at the moment. You can see me moving it here, but I want to discuss a few things. First of all, the Bode plot. The open loop Bode plot, or frequency response of a servo, a DC motor servo, wants to look something like this. This axis here is the gain in dB, and along this axis is the frequency, in this case in hertz. Often it's given in radians, but nothing's really measured in radians, everything's measured in hertz, so I do it in hertz, so you can do it in radians if you like. And the open loop Bode plot, it's always the open loop that determines the stability. Typically looks something like this. It's got a very steep slope at low frequencies. Let's call this low frequencies. It's all relative, of course. The reason it's got a very steep slope is because we want to reject disturbances at low frequencies. Ideally, it would be like a vertical line. So, but in this case, it's let's say minus 40 dB per decade, for example, and then minus 20 dB per decade as we go through unity gain. This is the asymptotic Bode plot, of course. The real one follows very closely. And then down to minus 40 again. This frequency here, where it cuts 0 dB, is called the unity gain bandwidth. It's very important, because the higher that is, the faster the response will be the servo. And that's very important if you've got an electromechanical servo, let's say driving a hard disk or some very fast electromechanical system. What they don't show you so much in the textbooks is over here at high frequencies there's a resonance, which varies of course from motor to motor and structure to structure. It's called the structural resonance, and as I'll show you, that's actually quite important. You have to be careful with that. You can't just do what you like with the Bode plot, especially if this peaks over, past the 0 dB. If it pokes its nose up here, you're going to get an oscillation at that frequency, even though the system's technically stable, because if you plot it the phase might do something like this. It might go along and go up and back down again. Along, up, down. So we arrange it so that the phase has got some maximum, something like that. It might start at minus 180, go up to minus 120, let's say, and then back down again. and then it'll shoot down the phase here at high frequencies. So what's important really is the phase margin that determines the stability. So here we go again, that's up and down, and maybe even down like that would be the phase. That would be minus 180 degrees. Let's say minus 120, just roughly. And the phase margin would be here. A good phase margin, so it's rock solid stable. But that doesn't mean to say that over here you don't get instability as well. So if this pokes its nose up here, you get a second phase margin which is unstable. So although it's stable here, it can be unstable here due to the oscillation. In amplifiers and so on, there's this called a parasitic oscillation. Here it's a lot more severe. You actually hear it and in fact feel it. And there'll be other resonances above that, as we'll see as well perhaps. Okay, so how do you control such a system? Well, the standard way of doing that is to, most people use a PI type controller. I'll look at that first, this approach here. This is a digital one, of course, but whether it's digital or analog, the principle's very similar, except for with one you're using Laplace, the other one you're using Z transforms and difference equations, which we are because it's digital. But this is the classic one with the proportional integral and derivative all in parallel with one another, and you have the error coming in here and the control going out there. I didn't actually implement, I did start off implementing it this way, but there's a slight problem with this approach, as we'll see in a minute. The other method, which is a bit more robust, is to do the PI bit and then put a phase advance after it, or a phase lead as it's called. It's a lot more stable and avoids problems with this resonance that I just discussed. Now, if you're implementing a very low bandwidth controller, which means a very slow system, and it's not let's say it's electromechanical system, then you won't have that problem. But most control systems, you want to make the bandwidth as fast as possible, as high as possible, so it becomes as fast as possible. So if you, in a PID controller, often many people just implement a pure difference, and you end up with a pure differentiator. Now you can't get that in an analog system, but in a digital system it's very easy to implement. But the Bode plot of that is a slope of 20 dB per decade in the magnitude, which keeps going up forever, well, up to half sampling at least, and then with a phase of plus 90. And with that constant increase in gain due to the differentiator, that in fact will cause oscillations in the motor, with the mechanical resonance. It'll excite the mechanical resonance. It makes more sense to tail off the differentiator and put a filter on there, so it at least flattens off, if not goes down, so you don't excite the resonance over here. If I go back to that, if you start putting pure differentiators in, this bit here pokes up. Now, phase advance is a bit smarter. You read about this in the textbooks. So, like a differentiator, it's got a slope of 20 dB per decade. Its phase goes up and down again, like that. And it's a band-limited differentiator, so it's not differentiating forever up in high frequencies. It's not doing anything at low frequencies. And because I'm putting it in cascade, that means I'm putting it in after the PI. Not in parallel. I can it'll work really well, I hope. So let's have a look at the real thing and see it working. So I'm going to, I've already seen the real thing. I'm going to put in a square wave to excite it. Oops, let's do this again. So set point, it's better, right. There we go. So it's a bit fast perhaps, but go back to the motor. You see the motor's going back and forward because I'm putting a square wave in. It takes a fair whack of current when it's doing that. 10 amps maximum. And there's the PWM as it's doing it. But it's tracking reasonably well. There's the waveform coming out of the tacho, that's to say the quad detector. You see you've got a little bit of overshoot. But it's not very fast. The rise time, I don't know if you can see it, it's because I haven't increased the gain. If I make the gain higher, this is like the proportional gain, what happens eventually? You begin to see a little oscillation appearing. You can hear it even. There it goes. Not very nice. That's our mechanical resonance being excited that I just mentioned. I mean, it's pretty nasty actually as you go up. It'll draw quite a lot of current, so I don't want to make it too much. Now the integral part I'm going to increase. Now as I increase the integral part, why would I do that? Well, the integral part, it controls the gain at low frequencies, and the higher the gain, the better the disturbance rejection. So it's actually a good thing to have an integrator or two. There's already one integrator due to the fact that there's a quad detector in there which acts like an integrator going from velocity to position. Now if I increase the integral action, which is nice to have allow you to do that, you see that the overshoot increases. So this is not a simulation, this is the real thing. You can hear it. You can see sort of overshoot there, beginning to get severe there. So you can't put too much integral in, otherwise you can see what it's doing. It's beginning to completely oscillate. Oh, there it goes. Push it down. So we need to find a sort of happy medium for that. Here's the phase advance, which is set at 60 Hertz. That was a bit of trial and error there. So the other thing I wanted to show you was, apart from the structural resonance, was to put a sine wave into this. And put a sine wave into it and increase it. You need to make it quite high and see what happens. Oh, you can hear that. And the whole motor bursts into voice. It's pretty nasty. I think you'll agree. I'm going to turn that off now. But that illustrates the structural resonance of the windings. It's a sort of the windings of the motor. So that's probably beyond the initial mechanical resonance. There's some other resonances as well. And in fact, it's these terms that restrict the bandwidth of any electromechanical servo. Again, the thing that's not really mentioned much in the textbooks is what restricts the bandwidth. This is the bandwidth here of a servo, and the answer is these resonances. Different for every motor. If you want to make it higher, you get yourself, let's say, a better motor with a higher structural resonance, different mechanical characteristics and so on. So that controls the speed. Faster the better. Phase margin determines the stability. If you drew the phase there, you'd have to peak up above 180. The low frequency part determines the disturbance rejection properties and the tracking ability, in fact. You can have one or two integrators. In this case it's two integrators. If you only had one integrator down here, the slope would be much less. If the slope is less, that means the gain is smaller, and so the disturbance properties isn't as good. It doesn't matter the fact the slope is, if the slope is more severe, it means you get more phase, of course, negative phase, but provided it's far enough away from the unity gain crossover frequency here, you're kind of alright. This frequency ratio of that one to that one across the span, as we call it here, is known as the span ratio. And the span ratio is also in the phase advance, the ratio of that guy to that guy. So in this case I've made it 10 to 1. I made the span ratio 10 to 1, and I've made the center frequency here in the phase advance about 60 Hertz, let's say. So it senses in 60 Hertz. 60 Hertz is for a big motor like that, it's not too bad a bandwidth really. It doesn't mean you can track signals up to 60 Hertz, of course, because it loses gain at 60 Hertz, but you know, maybe up to 6 Hertz it's going to do quite well. You could push for a higher frequency, a higher unity gain. You're always fighting against the structural resonances, however. So I hope you enjoyed that. It's a little bit about the practical aspects of implementing a DC digital position control system, and looking at the limitations on bandwidth caused by structural resonance. Thank you very much.